work? Okay. Yeah, thank you, Pieter. So today I'm going to mention about improved cadastral data management tools that we developed. And I will start first with the motivation. So our motivation is also embedded in the title. So we are developing this tool for flood risk management. As you are all familiar, urban flooding is on the rise. Rainfall are increasing. We are having more extreme weather events. Sea levels rise, and we have bigger cities now, which also makes it a challenge. Especially for the Netherlands, since it's 65% lies below the sea level, it's quite critical. And yeah, Netherlands deals with this for centuries, but they are increasingly switching from centralized to decentralized strategies. So the official name of the strategy is multi-level safety policy, which empowers local actors and municipalities. So along with the national dikes, there are like community scale flood defense mechanisms, which I will mention what they are in the next slide. And you are all familiar. We have a lot of data in silos. We have cadastral, parcel data, 3D city models, BIM. So, but there's no common language. It's hard to bring data from one scale to another. So very quickly, I will give a example. So city of Dordrecht, it's a small city that is located in an island that is surrounded with rivers. And yeah, they are all, the city is vulnerable in terms of river flooding, also storm surge, and pluvial flooding. So there is a traditional defense, which is the dikes, that is run by Delta Works. But increasingly, the municipality and the local governments, they are trying to come up with flooding defense mechanisms to channel the water so that there's no full-scale flooding. And these are like temporary structures, but also they can be a part of your building. It can be a wall in your building, and sometimes even the local owner of the building doesn't know this is part of the FDM. And this is a challenge for the municipality. They need to check it to see nothing changed. So yeah, there is a potential. We have the 3D city model data, the city scale data, and we have the building scale data, and we want to combine, but it's not always easy. There are challenges. They are inherently different things. So city models, they are using global coordinate systems and simple geometries, whereas building BIM uses local coordinate system and they are more complicated geometries. So working with these two data, there's a possibility to lose semantic information and also the geometry information. So there are, of course, plenty of different people coming up with potential solutions. There's 4 that is listed. So conversion of existing standards, transforming IFC to CTGML, which is generally used for visualization, and yeah, there's the risk of losing semantic information and inaccuracies. You can extend the information model, but yeah, it can be complicated, and there's always limitations. Integration at the application level. This is generally like custom application, so it's generally proprietary software that's handling, and yeah, there's lack of flexibility. And finally, integration at the process level. So information stays in its own format, and web services or platforms links different domains. So we are using this integration at the process level for this tool. So yeah, the tool is for improving cadastral data management for flooding. So it's a unified web tool, and the aim is to bring BIM-GIS cadastral layers in one web application, and the backbone is semantic web. So RDF Sparkle links parcel, building, and FDM data, and it becomes a knowledge graph. And so the aim is to also have a two-way engagement. The local owners can submit and municipalities can validate information. We define two user roles for this, property owner and municipality officer. So the property owner can log in and locate the property and upload IFC and enter the FDM specs and modify it. And municipality officer can check this and run some queries and approve. And then this ensures that there's a single source of truth and it's stored in a federated graph. So it's shared and single data. So yeah, very briefly, this is the system architecture. So in the backend, we are using Django, which is a Python-based web framework, and it uses the model view template structure. So we have 4 applications that are in connection with each other for login, for showing the city viewer, the Cesium map, and for running Sparkle queries, and to upload IFC. And the front end is handled by the template of Django. So we have the Cesium part where you can go and interact with city and city viewer, or we have also the IFC viewer. And in the data layer, we have Cadastral DB. So this is a Dutch organization that you can access 3D tile as geometry, and we show that in Cesium, but also you can access bag vocabulary and you can run Sparkle queries. And we have 2 databases, GraphDB and DjangoDB. But yeah, this is SQLite, but in production generally it's Postgres. For this case, it was SQLite. So this is the bag vocabulary that we are using. So it can be used to search addresses or certain other fields. And the core thing is the alignment. So the way that it works, we have the bag, and in bag we are using bag pond, and it's aligned with the bot building. And for this, the IFC is converted by a script that I think Pieter developed. So this is the database structure. We have the IFC, and it's linked to IFC RDF, and then FDM RDF. And yeah, this is linked to Cadastral DB. So I will, again, very briefly show the use case. So this is so the property owner and municipality officer. There's the login, search, and uploading IFC, and then a municipality officer can inspect the building. Again, very quickly, this is how query works. You search address, it's converted into Sparkle, and you can get the result from bag. And this is the user interface. You can enter in the fields, and then you can find, and you can also find your building within the 3D viewer. So this is how you upload and view IFC. So you can click the building, check if IFC exists. If it does not, you can upload it, and it's stored it in DjangoDB, and also it's converted into IFC RDF. This is for defining FDM. So you can go to IFC viewer. So it looks like this. And yeah, you can define, select the building element and mark it as FDM. And so this was the property owner part, and the municipality officer can review and approve this. So he can click the building updates, query FDM, and inspect it within the IFC viewer and approve the changes. And this is then converted and stored as FDM RDF. And lastly, yeah, the municipality officer can do a bunch of queries within bag, and also with the IFC RDF and FDM. So yeah, this is mainly the tool that is developed. Yeah, we have some, mainly we achieved what we were aiming for, but there's still some limitations, so especially the visualization. So the FDM wall is not, we are not able to view it independently from the IFC, so you need to go to IFC viewer and you cannot see it in the Cesium. And currently it's only one-way workflow. The owner submits and the city can approve. There is no version history, so that was the aim intention, but yeah, it's not done. And sometimes it breaks and it's not possible to import, so we need more strict validation and lighter ontologies. And yeah, so yeah, this was a tool to bridge theory and practice. And yeah, it has a potential real-world impact, but yeah, sadly, it's not actively developed at the moment. But if there is some development, the focus will be on versioning and on the visualization. And thank you. If you want to see reach to the code, this is the GitHub. So you can check it.